Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. So we continue this lecture with this Green's equivalences. First we recall the minimal element of a partially ordered set because we are using that the minimal element in our coming results. So let's recall that the minimal element of a partially ordered set. If X with this partial ordering is partially ordered set, then an element A belongs to X is said to be minimal. Is said to be a minimal element. Is said to be a minimal element if there does not exist any element which is strictly less than A. In other words, if for all y belongs to X with y less or equal to X, with y less or equal to A implies y should be equal to A. So there should not exist any y which is strictly less than A. That means if for any y less or equal to A, this y should be equal to A. Then we say that this A is a minimal element of X. Okay? And if the partial ordered set has a minimal element A, then we say that this X satisfies minimal condition. In case if X has a minimal element, then we say X satisfies minimal condition. Then we say this partially ordered set X, it satisfies the minimal condition if it possesses such element, minimal element. Okay, now let's come back to this Green's equivalences. So we have defined A relation, R relation, D relation, J relation. So let's define those sets. Say S over L. It's the set of all equivalence classes generated by this relation A. A belongs to S, and we have S over say R, which is equal to the equivalence classes generated by this relation R, and we have another set, let's say H, which is equal to the H classes. Okay. And we have one more set that's S over J. S over J, that's equal to J classes. And finally we have D, which is equal to the T classes. So these are quotient sets actually, and we define an order on those sets so that they will become a partially ordered set. So let's define order on this. We say LA is related to LB if and only if, because this relation depends on the principal left ideal. We can say it's lesser if and only if the principal left ideal generated by A is subset of principal left ideal generated by B. That's the relation on S over L. Then it will become a partially ordered set with respect to this relation. And on S over R we define the relation. We say the R classes, they are related to each other, or in RB, if and only if the right principal ideal generated by A is subset of the right principal ideal generated by B. And on the H, in the similar way, it's actually the intersection of these two, so it's a partially ordered set. So no need to define here. Now on S over J, we define this relation by because they are two solid ideals. Okay, we define these the J classes, they are related the G class B if and only if the two-sided principal ideal generated by A is subset of the two-sided principal ideal generated by B. Okay, and this D is the join of these two relations L and R. So these are the partially ordered sets. Now we define another class of semigroups where D is equal to J. That depends upon the minimal condition actually. So let's define that. So there are S over L, S over R, and S over J. They are partially ordered sets. And if these partially ordered sets, if they satisfy minimal condition, if S over J, if S over J satisfies the minimal condition, let's if S over L, S over R, S over G satisfy the minimal condition, satisfies the minimal condition, if these partial ordered satisfy means they possess minimal elements S over L, S over R, S over J. If they possess minimal elements, then satisfy the minimal conditions on principal ideals. Okay. Then we say S satisfies. Then we say S satisfies minimal L. It's capital L, minimum R, and minimum J, respectively. Okay. So we say the semigroup S, it satisfies minimum L condition if S over L satisfies minimal condition. That means if S over L possesses minimal element. Similarly, we say S satisfies minimum R condition. S satisfies minimum R condition if the semigroup, if this partial ordered set S over R, it satisfies the minimal condition. That means it possesses the minimal element. Similarly, for this minimal G. Now, next theorem is very important. If the semigroup S satisfies minimal L and minimal R condition, if the semigroup S satisfies minimal L and minimal R condition, then the D relation is same as same as J relation. D is same as G. So I will leave the proof for you. So and you can see its proof at page number 48 of this fundamentals of semigroups. Okay, page number 48. You can see its proof. It's very simple. So next we discuss the structure of Deglosses. Okay. Structure of Deglosses. Structure of Deglosses. Structure of Deglosses. Okay. let's first prove that every D class exercise. Let's show that every D class is union of L classes, or it's also union of R classes. Show that every D class, equivalence class generated by D of every element is actually union of L classes. So solution is very simple because we know that for all x in X, the D class generated by X is subset of it's L class. L class is always subset of D class. L class of any element X. Okay? L class of any element X is actually subset of D class of X, so you can easily verify it. So you choose any element here, you need to prove that that element also it is D related to X. It's simple because if it's L related to X, it's always D related, as D is actually the least upper bound of L and G. So this is always true. This is always true. This implies if I take the union over L classes where X runs over the D class, X runs over D class, say DA, D class of A, it is subset of union of D classes where X runs over D class of A. Okay, and on this side it's equivalent to the D class of E because you are taking union over D classes actually, and X belongs to D, so it's always equal to D. It's always equal to DA. And on this side, this unit, it at least contains each element of DA, because suppose we have say three elements in DA, say A1, A2, A3, then it will be LA1 union LA2 union LA3. LA1 contains A1 because A1 it's an equivalence class, so it must contain A1. LA2 contains LA2, LA2 contains A2, LA3 contains A3. So that means this unit contains at least those three elements which belongs to D. So it means that this DA is always subset of this union, so which implies that DA it's always subset of the union of L classes where X belongs to DA, and this is subset of DA. It's true for each A S actually, so which implies this DA is actually its union of L classes. So D class is union of L classes. Similarly, you can prove that D class is union of R classes. It's very simple. Now one more exercise for you. It's the intersection of L class and R class. The intersection of L class and R class is either empty or an H class. So if it's empty, then there is nothing to prove, but you assume that the intersection, say LA and LRB, they are this is an L class, this is an L class, and this one is an R class. You need to, if this is non-empty, if X is in there, then this should be equal to some H class. So it's equal to some H class of some element if it is non-empty. If it is non-empty, the intersection of L class and an R class is either empty or an H class. Okay, and one more exercise. If LA intersection RB is non-empty, it's true. This is true if and only if A and B they are derelated. They are derelated, or you can say A is derelated to B. Okay. The intersection is non-empty if and only they are derelated. So it's again simple, because if they are non-empty, so X is there, X is in LA, X is in LB. That means X is related to A, X is related to B, which means A and B they belong to L composition R, but L composition R is D. So that means A and B they are derelated. And conversely, if A and B are derelated, D is actually L composition R. So A and B belongs to L composition R. It means that there exists C such that A and C belongs to L and C and B belongs to R. So that means this C, it belongs to LA as well as LB. So which means C belongs to LA intersection LB. That means L class and the R class generated by A and B respectively. The intersection is non-empty of these two classes, L class of A and R class of B. So it's again simple. It's again simple. So let's now we have now which we try to prove a very important theorem that's called Green's lemma. Before proving Green's lemma, we to discuss a map first. That's called a translation map. You can write translation map actually. So what's that? Right translation map and left translation map. Right translation map. Suppose A and B they are if they are in D, they are in some D class. So let's suppose that let D be an arbitrary D class. So it is some D class. So it's an equivalence class of some element with respect to the relation D class. And if A comma B they belong to this D class, okay, such that A is R related to B, such that A is R related to B, then by definition there exists S and S dash, S comma S dash in the semigroup S1, such that its right side AS is equal to B and BS dash is equal to A. BS dash is equal to A. Now let's define a map. Define row S from S to S by row S of any element, say X, equal to XS. X is an element of S. S is also an element of S. XS. So then this row S, it maps A onto B. Then row S of A, it's equal to AS. That's equal to B. So that means that's row S maps A onto B. So this it's called a right translation. Okay, right translation. It maps A onto B. In fact, we will see that it maps LA onto LB. It maps LA onto LB. And similarly, we can define the left translation where we say this A and B, they are in some D class such that A is L related to B. Then I can find S and S dash such that SA is equal to B and S dash B is equal to A. And in that case, we define a map rho of S dash from S to S by rho of S dash of X equal to S dash X. And you will see that that map maps B onto A. That you can easily see. So, and we'll also see that that maps actually maps LA onto LB onto LA. Now, first we will see that we check the properties of this map, and the properties of that map follows similarly. So, let's first check that this right translation, it maps LA, the L class of A, onto onto this R class of B. Okay, it maps L class of A onto L class of B. Okay, we'll show that it maps L class of A onto L class of B. First property, rho S maps L class of A onto L class of B. L class of A onto L class of B. Okay. So let's choose any element here. We'll show that the image of that element under rho S is here. So let X belongs to LA. So it implies that X is related to A. So this implies, since this L relation, its right congruence, so it means that XS belongs to, or first I will write it as X comma A belongs to L, which implies by right translation XS comma AS belongs to LAS. So that means this XS, it belongs to the L class of AS. Okay, because they are related to each other, so XS belongs to the class of AS. But what's L of AS? It's actually B. LB. And what's XS? XS by definition it's equal to rho of XS equal to XS. So which means that rho S of X, it belongs to LB. So whenever X is in LA, its image under rho S is in LB. So that means it maps LA onto LB. So therefore rho S maps LA onto LB. Therefore rho S maps LA